Hi, everybody. Good to be here. We're going to have fun up here for the next hour, and I hope you're going to have fun with us. This is going to be a bit different from what you're used to, of course, because it's Pattern Computer. So I'm going to talk a little bit about patterns, so if you're new to the whole thing, you'll get a bit of a taste. And then we're going to bring you our whole team, which is sitting right here, or the team that's in San Diego at the moment. And we'll talk about things that are near and dear to our heart. There are new achievements and new milestones. And that kind of opens the door for me to talk about my view, and you've heard some of this yesterday, on where things are in the landscape of the world in terms of AI. AI should not be the same thing as large language models, but mostly it is today. When people hear AI, they don't know very much about it. They tend to think they're equal to each other. They aren't, but in practice, they kind of are right now. At Pattern, we don't use large language models. There's a reason for that, and that leads to this question of what is the landscape about. I think it's kind of fun. One of the fun things at FIRE is things are happening around us, outside of us, in real time. So yesterday when I said to all of y'all that Apple and Amazon and Microsoft were fighting this battle internally to protect their brands from the future damage caused by LLMs, well, now it's today. And Apple has just had their Worldwide Developer Conference yesterday, and for 10 points, how many people know how much time they spent during the entire day on OpenAI or anything with those words or LLMs? Yeah, 0 is the answer. Thank you very much. So we're seeing that prediction got ratified in real time. And the brand stands and they still have a company. It's great. So this landscape is fraught. And the people at Apple are not stupid about brand. They're probably the best in the world. And they understand the exact risks they're facing. And therefore, they and Microsoft and Amazon are being very, very careful about getting anywhere near the words that are going to blow up, or the brands that are going to blow up, or the actual products that are going to blow up. And therefore, they will survive. And if you heard the Wall Street Journal or listened to the Wall Street Journal or read the Wall Street Journal this morning, which I did, nice guy named Dan wrote this beautiful story about how stupid Apple is. No, it's the Wall Street Journal that's stupid. So there's a lot of confusion out there. But at least from our perspective, we are fortunate that we chose in the very beginning to roll our own. And so with Ben's help, actually, back when he was working at Berkeley Labs, he gave us some hints about where to start. And he was right, of course, as usual. Weird thing about Ben. And so we did that. And we spent 3 years in secret. We wrote our own mathematics with his help. We wrote our own software. We created our own architecture. Everything from, we didn't make any chips, but everything down to making chips. And the result was we're completely isolated from that issue. So I'm going to move for a moment from the AI landscape to the pattern landscape. We have our own landscape, and it's pretty interesting. So when we take these tools that Ben and everybody else on the team has created and apply them to real-world problems, we look different from, we all go to a lot of meetings, right? I can't tell you how many conferences and meetings I go to every year, and Denise goes to, and Ben goes to, a lot, all over the world. We've got friends from Hamburger here. We go all over the place, Stockholm, we go to Ireland. And let me tell you what it's like out there. You hear and see, you go see posters and you see talks, and the leading guys in the leading thing, and they say, we hope to soon discover drugs. Good idea. We know that in the future, this will be a boon to medicine. It'll be a revolution. Sounds good. They're not doing it. They're selling it. And selling ain't doing. So I'm proud to say that today we're going to do what we do every day, and we're going to share real things with you guys. And so what we'll be talking about are actual things that we've already built or already discovered, that have already been used to solve problems. It's in the past tense in general, except for one thing we'll share with you. And so I'm very proud of that. and it really is who we are. We don't do a lot of bragging, except when we're with our investors in a meeting, which we'll do with you tonight if you want. But basically, we do the work. And all the people you'll see are of the same exact persuasion. They're brilliant. They do hard work. They don't complain to me about very much, but they probably complain to each other. But they do the work. And the result is we got really cool things to share with you. And we're not going to share them like someday maybe we'll do a drug. Just the opposite, as you'll see in a few minutes. So I think with that, I'm gonna stop my grandstanding here. I'm down to 5 seconds. And I'm going to introduce you to Ben Brown, Dr. James Ben Brown. There's another Ben Brown in the audience, and you're going to meet him sometime today, I think. And Ben is, as you'll see, much more eloquent than I am about these things. And I love working with him because we go on the road together, and we talk to guys like VCs or experts in tech, and it doesn't take more than about a minute before I go, well, Ben, tell them the answer. So Ben's going to talk to you about the discovery engine. So our pattern discovery engine is it's a bit of a head fake because it changes every day. And at any given moment, if you looked at the internal map of all the technology, it's like 50 pieces. But we call this the pattern discovery engine. And we occasionally kind of freeze everything, and it's got a product number, a version number. So with that, Ben, would you help these people understand what is it, and what is the difference between LLMs or today's other AI products and what we've done?
Sure thing. Thank you very much, Mark. Appreciate the intro. So working with Pattern is an absolute pleasure because the mission statement from day one was to develop bespoke technology that is useful for making discoveries, for discovering patterns and guiding principles from some of the most complex data on the planet. And that is a very different aim than if you're trying to make something that will do a nice job of drawing pictures of cats for you or do a good job of answering your customer service hotline. Those are very different tasks. And with large language models and generative AI, and the generative AI revolution, and make no mistake, it was a revolution, and it's affected many industries and many areas of endeavorment in very serious ways. But that revolution was not a computer science revolution per se. There's nothing particularly novel in the architectures. It was a data revolution. It was the fact that all of the common crawl could be assembled in one place, and you could have 4 billion web pages that you could use to train a model. With DeepSeek and other models that's gotten even larger, the DeepSeek was trained on something 4 times larger than the common crawl. And so that capacity to assemble data sets of previously inconceivable scale, the sum total of all human knowledge, is remarkable, and it's a paradigm shift. But what those models do, those architectures do, what the generative AI architectures do, is based on a query or based on a prompt or based on the stuff they've said previously, they predict what's the next most likely thing I'm going to say. And for those of you who had applied math in the 90s, Markov process, it's just learning the next token from the previous ones. And that has no intrinsic hedge to problems like hallucination. So if you want to apply your large language model to a high-risk application area, it's a very dubious thing to try and do. The Office of National Nuclear Security, the Department of Defense, and many others have declared these things unfit for any mission needs. And that's because you can't put those guardrails on them. Pharma has spent an enormous amount of money in the past 18 months trying to put various types of guardrails on large language models and diffusion-based models to do drug discovery, stuff called retrieval augmented generation, where you force the large language model to associate a database reference with everything that it spits out. Problem is it can just hallucinate those just fine too. And so we're in a place where you have an architecture that looks very interesting and can do undeniably amazing things. I mean, look at Boltz 1 for predicting protein small molecule conformations. It's amazing. But that fundamental problem of hallucination is there, and the fundamental problem of being a black box is there, right? The AlphaFold 3 probably knows stuff about soft matter physics that we humans don't, but there has not been a way to get that knowledge out. And understanding not just the capacity to predict, but why prediction is possible is the primary driver of science, right? That's what we do. And with Pattern, that's what we set out to do. We set out to learn engineering principles, learn scientific principles from data. So not just patterns that exist in data, patterns in data that inform about processes in the world. So everything here is built from the ground up to be interpretable, to be causal, to find stuff that generalizes far beyond the data that was used to train it, right? You want to learn the laws of physics. You don't want to learn Copernican epicycles. You want to learn Newtonian dynamics. And so it's been the guiding principle for Pattern. And with the Pattern Discovery Engine, we have now packaged that into Pattern DE, which folks can come and use. And you're going to hear a lot more about it today from Quinn and from others. But getting this capability into the hands of academicians is very important to us. We want to see this technology deployed on the most challenging research problems of our day. And we have recruited a set of alpha users who are now making use of this technology to tackle research problems of profound importance. One observation from one of our alpha users was that the SARS-CoV-2 mortality rate was about a 10x to 100x higher depending on the soil microbiome of the surrounding area. And the fact that the soil microbiome was more informative for mortality than public policy or socioeconomics put together is really interesting, and it'd be really nice to know why. And they have a nice predictor that maps soil microbes onto predicted health state, but they don't know what causes it. And so this is something where the Pattern Discovery Engine can come in and give you some insight into what's actually happening.
So I think you just heard 2 announcements, but many more to come. And we are right at the point where we probably want to be joined by somebody else. And by the way, if I fall asleep on stage today, it's because of this fellow who we spent a long time talking about physics last night. Ian, welcome.
Thank you.
And Ian is from Basel at the moment. And would you like to tell them about your background a little bit?
Yeah, so I've spent my career in pharma on the commercial side and in development, and then moving across into medical devices and advanced diagnostics. So spending a lot of time helping the companies in cancer work out how to apply comprehensive genomic profiling into the clinic, and then more recently how to use those technologies to bring screening assays, so for people that don't yet know whether they've got cancer or not, and defining whether they do or don't.
Right, and Denise and I met Ian through a mutual friend in Basel over a lunch or something, and we've been talking ever since. And he's on our advisory board now, and he's been kind enough to come here from Switzerland, so thank you for that. And he's going to talk about what we call Project Starbright. And as those of you who know Pattern know what that means, but we made a project which was pretty outrageous, I got to say, for a newbie kid on the block to say, let's go after the top 5 cancers in the world and see what we can do to move the needle on those different diseases. And that's been quite successful, as you can see by this chart. So we won't spend a lot of time on this, but we now have, there were 5. We have 1 that we took off the list for various reasons, and we've added 3 or 4 more. So now it's probably 6 or 7. And what you're seeing here are essentially 22 pipelines of drugs. A pipeline is a drug being tested from 0 to 60 kind of thing. So would you want to talk about Starbright and where you think we are and talk about the industry and kind of why is this special? What are we doing that's better than what somebody else is doing?
I think if we go back to the prior slide just for a second, because it came up briefly, I think it's very impressive to see so many possible active compounds coming through a relatively small program up until this point, so that you have a hit rate for in vitro and now in vivo activity from one program, which is so promising, is incredible. And I don't think that that's been seen in many of the other attempts to use AI or some form of AI. Apologies for using that word. I know it's a sensitive topic. So this is incredible, first of all. So if we move on to the next slide, I think the question now for Pattern is how do we get that knowledge of what is possible, what kinds of problems are tractable now using this kind of technology into the minds of people that can make decisions about it. And so what we're working on together is how do we increase the level of engagement with academia to make sure that we're working with people who are well respected in the field. As you just heard actually from the sofa, the role and the relationship between the institutions and the drug companies is very important. The institutions tend to be working on the core biology problems, getting those translated into pharma, and then the pharma companies are working on these enormous trials. And so the questions that we need to get into people's minds are, how can we help? And I know we've spoken a few times about this, but if we can help in terms of identifying synergistic combinations, particularly where one of those molecules has got a long patent life, could really augment value for the pharma company economically, but the synergistic combination could be transformative in terms of efficacy. That's a well-established principle, particularly in oncology and other places. We've seen a lot of areas where targeted therapies have been pretty good on their own and then really good when you put them in combination with something else. And so if we're able to amp that up, that could be a really big value driver for pharma, could be a really big value driver for patent. Mm-hmm. And then I think there are other possibilities. If it turns out that the data's available to be analyzed with a system like yours, and it has the possibility of improving the likelihood of good effect and the likelihood of not causing significant side effects, then you could start to move the needle on one of the most difficult problems in pharma, which has been how do we predict the probability of success or influence the probability of success at different stages of development. So even today, I don't know what the latest figures are, but when you're early in development, you're probably only still carrying a 5 to 10% chance of success, which gradually increases as you go through clinical development. If you can move the needle on that, that's one of the most important drivers of value in pharma.
And does it look to you as though we have the tools we need to do that?
I think so. Yeah, I think that's why I wanted to go back to that original slide. That you've certainly got a very strong signal that you have that capability.
Yeah. Well, thank you. I see we're down to the next thing. So I appreciate your time. Thanks, Ian.
Thank you, Ian.
Take that.
KKD, we call him. This is his home turf. I first met Ken upstairs
Yes, we did.
a little while ago.
Yes, we did.
And when I met him through Larry. And Larry had kindly arranged a half-day or a day-long thing. So we're setting up this laboratory, and here are all the people Larry was suggesting ought to be involved in a pattern recognition lab. And this guy, we're kind of tired. It's like noon. And Ken shows up, and he immediately starts a lecture with a blackboard. And he has his own complete Ancestry.com of everything in AI, and he shows us how it's structured, who's leading it, what's the mathematics, how does the math work, questions please? And it took a half an hour. And we were like,
Wait, we only got 5 minutes.
who is that math man? So welcome.
Well, thank you.
Yeah, and Ken's going to talk about something which we call adaptive example selection, and it's brand new. We've just published a paper, I think, on that.
We're just about to
There you
publish
go.
a paper, yes.
And which happens pretty often these days. So would you please explain to the folks here, what is it? What is AES? Why should they care, right? And what does it do?
Okay, it'll be fun.
Yeah.
As Ben mentioned, a lot of our product from the very beginning is designed ab ovo from the beginning to provide explanation. And Ben has discussed the path-breaking work we've done in that regard. But a lot of the stuff you get on public domain and can purchase from companies is already pre-trained, and they're not openable. They can't take the black box and turn it into a glass box. And so we're actually doing a lot of work on general approaches to open up an arbitrarily pre-trained, already utilized neural network. And Luca will talk to that later, I believe.
Yeah.
But we're focusing on a situation where we are looking at a special, very pedestrian almost class of pre-trained neural networks that are trained on data that's directly comprehensible to the expert. For instance, in radiology, a radiologist can look at an image and immediately they understand what's going on. It's grokkable data. So let's call it grokkable data.
And we're trying to solve a problem here, which I happen to know about.
Yes.
But I'd like to share with them. So the
Right.
problem is when the industry looked at itself in radiology and pathology, they came up with the understanding that there wasn't very high usage of AI even when it was available.
Exactly.
And the reason was they didn't trust it.
They
And
don't
the reason
trust
they didn't
it.
trust it was because they didn't understand why it was doing what it was doing. It was a black box.
It was a black box.
Go for it.
Yes, and the question is, some black boxes can be opened up in more direct ways, though still mathematically sophisticated ways than what Ben and Luca are trying to do. And so what we're doing is we're trying to say, if you're an expert and you instantly understand, because you're a radiologist, in our case, we're looking at histopathology and we're trying to understand when cells undergo mitotic division, because rapid division it basically is a strong indicator of cancer. When you're trying to understand when cells are undergoing mitosis, an expert can look at the image and go, wow, it's undergoing mitosis. So the expert knows. So the question is, if you have a neural network that's trained on data that an expert immediately understands, why can't you give an explanation in terms of those things that that expert, that radiologist, that histopathologist immediately understands? So what we've done is we've created this algorithm, call it adaptive example selection, where the radiologist says, look, I don't trust this thing. And we say, we can actually train on that black box to open it up, to show you, in terms of examples, you immediately grasp. Because, say, you're a professor at the medical school and you teach the next generation of young medical doctors, this is what it looks like. That's how you explain what's going on. They instantly understand. The expert immediately understands.
So the system shows you a picture that you understand.
It shows a
It's a
picture.
it's a real image.
It's a real image,
Yeah.
and it shows a cloud of nearby images. And what you can do is you can open up, you can query that pre-trained algorithm, and what it'll do is it'll show you a decision it made, and it'll also show you a surrounding cloud of nearby real-world examples, and it'll show you the decision the device made on those. Now, you, the expert, will know the actual images because this has been labeled by images. So you can develop confidence when you see that the device is actually reasoning the same way you would. This looks like cells undergoing mitosis. It's telling the truth you grasp.
And so the hope and the dream and the goal here is that instead of 5% or whatever the number is, pretty low, of pathologists using AI to help identify those cells, maybe it'll be 50% or 90%.
Or more. So what happens is you see here on the middle one, you see we want to think like the expert. That's what we're saying. This is how the expert thinks. They understand it. They don't have any doubt. I am the expert. I will tell you this is the truth. But you might want to tweak that algorithm. You might want to adjust it or adapt it. So the interesting things are those ambiguous decisions you have to make that are on the boundary. So we can actually do this decision boundary analysis. We give the user the right to kind of play in those nebulous regions in between where you don't know definitely yes or no. And you can play in a way that you're saying, I'm satisfied. This is as good as I believe an expert can get. If I were teaching students in medical school, I'm their instructor, I would be happy if a student understood those boundary cases and could do as well as this thing could do in those boundary cases, then I would pass this in my medical school class. This device then is a successful student. Let's free it to do medicine autonomously because I can verify and justify it. I trust it. In the court of law, I could say, of course, it's doing the same thing I would do as an expert, Mr. Lawyer, if I was being queried as to why that decision was made. So we, even though it's not as highfalutin as what Ben is doing, we think this is a breakthrough approach for those class of algorithms which are trained on directly understandable, directly interpretable, grokkable images or types of data that has that direct interpretability, apprehensible concept.
I know we're over time. I just want
We
to
are.
say one
Yeah.
thing,
Go.
just so quick. Ken, that was amazing. One of the reasons this was such an exciting problem is the American Association of Radiologists a couple of years ago published a paper that was called something like, "Please stop claiming radiology is a success for AI." And they went over, all of the claim benchmarks and refuted everything and said, it's not fit for purpose. And the problem was the same that Department of Defense had, that you're at a high risk decision making, and having something highlight a couple pixels for you doesn't actually save you 10 seconds of time in your diagnosis. And what Ken and team have done is create something that addresses all of those concerns and may actually be of considerable use to the radiological community. So it really is very exciting stuff.
Okay, we're done, Ken.
Okay, thank you.
Thank you, Ken.
Thank you.
Yeah, thank you. Serge Gart.
Good morning.
Good morning. We'll buy you some time on the other end here. Serge is our lead in prospectral. Many of you know what this is. Some don't probably have any idea. And so would you give a quick description of what prospectral is and then how it compares to the competition?
So let's pop up the next slide, please. So this here is a scan by the prospectral device of actual human saliva. Saliva is increasingly being appreciated for the number of biomarkers, hundreds of biomarkers for different diseases and conditions. And also can reflect that there's an actual host response occurring to a particular disease or a particular condition. All of these actually absorb light, but to various wavelengths and various intensities. And that in turn drives the shape of these traces and the fact that they grow with increasing exposure to light. So we think there are patterns here. And so we thought of starting to apply our pattern detection capabilities to try and establish signatures for specific diseases or conditions. Our first attempt was a few years ago, and a project at Los Alamos National Laboratories was able to identify frozen saliva from subjects with COVID with a 98% balanced accuracy. And that's as good as the PCR test. Since then, we then decided to broaden our scope, and last fall started a project at a major regional cancer center to try and detect lung cancer based on saliva samples. What's exciting about the past quarter is that we're very encouraged by some of the initial results. And we're very much looking forward to accumulating yet more data and refining our modeling of that. So that's as much as I would share about that right now, but it's quite exciting. The other thing that's quite exciting is some projects that are about to start, and that includes a collaboration with Phenome Health and at the Buck Institute that I believe Mark and Dr. Leroy Hood will elaborate on. So it's an exciting time for us. And if I can move on to that next slide, the other thing I'd like to point out, over on the right side, there are hundreds of biomarkers in saliva for various diseases and conditions. And on the left slide, there's just an enormous amount of biomarkers being established also for diseases. So there's great potential for us to go after and establish signatures for other diseases in saliva, number one. And number two, it's not just about saliva. We can also be looking at urine, at serum, plasma, et cetera. So we see a whole lot of potential going forwards with the opportunities that we create or come to us. And I know I just kind of went straight and talked a lot,
that's
but
good.
I thought I'd bring you some time back.
You did. You did a great job. Thanks. Goodbye, sir. No,
Bye.
no.
Oh, I'm sorry. One
the-
important thing. In a couple
Go.
hours, I'll have a device running outside. So if
Yes.
you want to come and kind of check it out yourself, more than happy to. I just need to connect a couple of things, and we're there. It's free
Yeah,
and
so
confidential, anonymous. So
there you go. So what you just heard was we're looking not only at communicable diseases like viral and bacterial and fungal, but we're now looking at cancer. We're working with the top person in the U.S., thanks to Ian, in human trials for oncology. She's an amazing woman, and at Medical College of Wisconsin. And we're now some ways into it. We don't have the full number of cases that we need to have to get up to 98, but we are showing very good results. I think it's smart not to give out numbers, but they're great numbers for the limited number of cases we've got so far.
And there's a little aspect of this that it's easy to not notice, which is this is all software based. We're not using chemical reagents. We're not throwing out tons of supplies every time there's a new variant, et cetera. We just update our modeling, issue a software update, and that's it. So it's a very different kind of test and with very different, the size of the device, the economics of it. There's a lot of things about it that are quite different from a lot of the established technologies and systems that cost millions out there.
And Ben's lab was one of the two testing labs, Los Alamos being the other one. Comments?
Yeah, so that one of my favorite things about this technology is that after minimal validation internally, Pattern just said, it works, handed it off to the national lab system and let them have a rip.
They bought it.
They bought it. They did, and seeing that external validation has been really tremendous in the stuff they've been able to do with it. They've got a wastewater program now where they're detecting analytes and toxins at very low concentration of wastewater. There's a program that is distinguishing viral from bacterial infection. Imagine in a couple of years when you go to your doctor, 2 drops of saliva, and you don't have to argue about whether or not you need antibiotics. I'm particularly looking forward to that. So it's an amazing device. Those squiggly lines you saw were about 10,000 individual analytes in saliva, by the way. So it really is cool. And if you want a snapshot of your health signature, you should go see Serge.
Yep.
So the really cool thing is go to see Serge out in the hallway during coffee or something.
Yeah.
Don't drink the coffee right away. First do the test.
Yep,
No chewing tobacco allowed. And
Well, you can try. It's an interesting it's a challenge.
we did that in Peru already. I think it was in Chile. So, but you will see something you'll never have seen before and may or may not see again. I hope you do see it again. You'll see the actual health state of your body. In other words, what Los Alamos tells us is that your saliva has essentially the same information that your blood has. But instead of taking a blood draw, 2 drops of saliva, and then in 3 seconds you'll see visually, what you saw here. And it will be a picture of every chemical bond in that sample of saliva, meaning every single molecule. So we don't know enough yet to then tell you you're going to die tomorrow or you're going to live forever, but we are working on what he described. And so you will actually be looking at something real about your own self for the first time ever in what your lab said later and published was likely to be the best point-of-care diagnostic tool in class. So with that, I'm going to say thank you, and on we go.
I think Luca's in Italy, so I can't. What do you want me to do with this, Luca?
Am I on yet?
You're on. You're on.
All right. Hello.
Where is Luca? Is he
But you
there?
guys can hear me, yeah?
We hear you.
We hear. Oh, there he is.
Okay,
We
great.
hear you.
And now we see
Okay.
you.
He's here.
Great.
Hi, Luca.
Hi.
He's in an undisclosed location. You can tell, right? This is our man in Moscow or something. So good to see you. It's a little bit later for Luca than it is here. So he's been kind enough to be awake while we're talking. And Luca, I understand you're working on a kind of a moonshot, which is actually his title.
Yeah, it's definitely a long shot, but we've made some good progress and had some exciting results to date that we've already shared them. Applying neural XAI to finance and to physics problems. But I guess to explain what it is, it's Pattern's approach to explaining the decisions that neural networks make. So, there are these opaque black boxes. They make decisions. They often have high performance, but you don't actually know what drives the decisions they make. And in some situations, that's fine. If the response is just supposed to help with something easy, low stakes, not a problem. But the fact that you don't know what drives the decisions, you don't know if a mistake that made will be repeated or if it was just a fluke. The fact that you can't guarantee that certain mistakes won't happen preclude it from being used in high stakes situations like medicine, law, finance, self-driving cars. There's a lot of examples. But those are places where it would really be nice to use them because they are often the highest performing models. Not always, but when there's a lot of data available, that tends to be the case.
And so you can see from the slide, we're calling this GAI, XAI. So generative AI, which is the stuff we talked about, the landscape earlier, LLMs and so on. And XAI is explainability or explainable AI and interpretability, which is what Ben was referring to. And Luca mentioned he's already done what we thought was kind of impossible, which is to take a regular old neural network, reach into its guts and prove you could see how and why it did what it did. And in one case, recreate the Navier-Stokes fluid equation, which is a crazy good thing to be able to do, based on data of a stream flowing around a rock. through a neural network. So we thought that he was wasting his time on things that were too easy, so we gave him a harder problem, which he's describing now. And so this landscape I described to you of carnage that we're facing in the future when people are recognizing the lack of trust they can have in their tools and the outputs of all their tools is coming right up. And Europe has a lot of rules about this. America has none, but it's going to be a big deal. So Luca has agreed to take on the project of can he extend his XAI abilities into that world? And so Luca, back to you.
Yeah, so we're now trying to apply neural XAI to LLMs. At its core, it's the same general concept, but it's obviously a lot harder. The models are much larger than the ones we were working with before. There's a lot of differences in the details of how they're applied, but those are things we're working on, and we've already made good progress on a number of them. And while a lot of this is forward-looking, it's still in progress. There's some really exciting possibilities, especially around hallucinations. I mean, there's no questioning that LLMs, compared to what we thought was possible 5 years ago, are amazing. But the hallucinations really throw a wrench in the whole thing, in the same way that not being able to see into the black box of neural networks does. So it's kind of there's two compounding issues here. But one of the potential benefits we see of the application of neural XAI to LLMs is the ability to get an idea of when hallucinations are happening. And obviously the approach we're taking is going to depend on whether the model is aware that it's not being truthful at the moment. And that's because neural XAI, the core concept of it is to use the model as a lens through which to view data, and that everything else follows from there. And so if the model is being untruthful when it's hallucinating, essentially bullshitting, then what drives the predictions it makes, the words that it's going to say, will look different from, or we expect will look different from when it's confident about what it's saying. If instead it's more of a delirium, that's going to be a little bit more difficult because everything it says, it'll think it's saying the right thing, and maybe that doesn't look different. But that's something that we're going to look into. And if it works out the way we expect, being able to either reduce the impact of hallucinations or possibly even make them detectable, makes the whole thing a lot more trustworthy. It makes the idea of agentic applications of AI, where you're taking people out of the loop, all of that becomes way more trustworthy, way more applicable, potentially even high-risk situations. But obviously, you want to take things slow for that. But it's a possibility.
So I think to put a slightly more financial twist into this story, if you imagine the number of universities and enterprises that have installed this bullshitty software, as he says, it's a very, very, very large amount of money been spent already, been hundreds of billions spent, more to come, and a lot of investment of time and energy and people, new products being created using this stuff. The embedded risk and the embedded value is extremely high. You could probably get a little bit braggadocio about this and say it may be one of the most valuable things you could do would be to save the world from the make up a name for this catastrophe when it happens, the trust catastrophe, and solve that. So Luca's not saying that we're going to solve it, but Luca, I'll put you on and we're about done here, but I'll put you on a softball question for you. Roughly speaking, in your estimate, how do you feel about our progress so far?
I will say good. There are still big hurdles to overcome, but there are significant hurdles that we have already made good progress on or solved at this point. So I think that makes me optimistic about the ones that we have yet to overcome.
Great guy. Thank you, Luca, and thanks for being with us from wherever the heck you might be.
Thanks.
Have a good sleep. Talk to you
Thanks.
soon. And that brings up the best dressed man in our team, Quinn. So, Quinn, Chief Scientist Mathematics. I always refer to Quinn as our orthogonal mathematician because he has this a wonderful kind of self-taught way of seeing things newly in new ways and finding discoveries about mathematics that were totally, to me at least, unexpected. So good to have you here.
Thank you. Good to be here.
What would you like to talk about this morning?
Well, we're going to be talking about pattern DE in this particular section.
What's that?
That's the hey Ben, what's pattern DE?
Pattern DE is, as I said earlier, that is the pattern discovery engine packaged for external users. So this has been a long time coming, getting it into a format that people can interact with. Pattern DE is now servable in two different modes. One is for an MBA type who wants to query something through a web interface, and another is via a Python package. So if you're a scikit-learn NumPy user, easy peasy. And we're deploying that with data scientists in the national lab systems of 3 countries, including this one, and about 7 tier 1 universities around the world. And it is working. People have been able to log on and have passwords and use it and stuff.
Eureka.
So we're very excited about that. And Quinn, tell us more about the guts of this thing and about what you're doing with it.
Okay, so pattern DE under the hood is the pattern discovery engine, and I want to emphasize that what's actually running online in pattern DE are the same tools that we use to make the discoveries in-house. So for instance, the Namida Lab breast cancer screening test, when we did that collaboration with Namida Lab, that engine was used, and that's exactly the same engine that's online. So if someone had a data set and the proper licensing, I will say that for Mark's sake, then they could upload and within 1 or 2 clicks develop models. That's the important thing. So the ability to have 1 or 2 clicks in machine learning, let's just say, okay, I learned how to started in data science on something called RStudio, the R program. Absolutely horrific. And Python is absolutely much worse. And I'm a computer programmer. I've been programming for over 25 years, and I like computer programming, but I hate data science programming. It's absolutely horrendous, the tools available. This is just a couple of clicks, and most of the defaults just work. The fact that most of the defaults just work in this system is the result of how much I hate actually having to tune hyperparameters. So the benefit others can have from that, but also there are going to be tutorials online because every scientist needs to know exactly what's going into the cake, right? So there are going to be tutorials online so that they can change the hyperparameters as they need to see how those can impact the results, and they can do their own hypothesis testing. The defaults won't work in some scientific contexts, and we'll have that for academics like Ben's friends. So that's basically what it is in a nutshell.
Is it restricted to any particular field, or is it?
No, the engines are absolutely domain agnostic. So you can use the same engines on medical, you can use it on financial, you could use it on predicting any number of things, like what Ben was saying with the bio, all of that can be done. And there's 2 main components. There's the dimension reduction and feature identification component, so if you have let's say 24,000 human genes and you're trying to find out which ones impact some particular diagnostic outcome, that's one type of tool, and it'll give you a list of just the factors that could possibly influence it. And the other one is a mathematical model generator that will generate a model, and mathematically you can see exactly how to make a prediction, and you know exactly what features are going into that prediction.
And one thing I like about the fact of it being online and available to anyone, there are actually a lot of things I like about that, but we have put in a bunch of data sets, I don't know how many, it keeps growing, where someone can come in, register, and use an existing well-known data set that they may have used them before in their school or something, and run again on the discovery engine, and see what happens to that same data that they couldn't do before, and therefore understand very quickly the beauty of that.
Or they
whole
could
thing.
see why we were able to beat the published results for something like
Yes,
the heart
exactly.
failure data set, and they can see it themselves and reproduce our results and change the hyperparameters and see if they can even beat
Right.
us.
Quinn wrote a paper about, we call 3 things, about published results, and then we took the same data and beat the pants off those people who published
Yeah.
that paper.
About
That's
that
why-
particular data set, we now are going to be looking at this risk confidence XAI. And that particular data set, now we don't just know how to beat the results, but we know how to give an actual confidence level on our prediction. And then that would allow a physician to be able to triage when they say that you should stay for further testing, they know exactly why.
Thank you, Quinn. Ben, comments?
It's amazing work. And I will say in the Alpha Users program, one of the recruitment criteria for folks was that they have a problem where existing methods have just not fit the bill. The problem has been recalcitrant to existing methods. They can't figure it out. And so enter Pattern DE and provide some nice closed form solutions that are easy for everyone to understand. So it's a very exciting time. Thank you for all your hard work on this, Quinn.
Thank you.
Now, that was Quinn 1.
Now we're going to go
Now,
Quinn 2.
Quinn 1 has left the stage, and Quinn 2 is back. Hi, Quinn.
Well, let's talk Wall
Welcome
Street.
back. He actually very cleverly segued into the next piece here. So this RC idea, this idea of risk and confidence, is leading to a new product.
Yes, risk confident XAI is something very interesting from the point of view of a mathematical equation. Now, in medicine, it's important to be able to say to a patient, the reason we're asking you to stay for further testing is because there's a very high chance you're going to die if you don't. But in Wall Street, there's should we trade on this particular entity? There's regulations. We have to understand risk when we make investments on behalf of people who have given us trust in their money. So the equations aren't enough. The fact that these 5 factors indicate that one should, purchase these shares, how often are we wrong when those specific inputs are used? That's the thing. Just having a general confidence interval is nice. 86% plus or minus 5, 95% confidence is great. But when this specific factor is increased, does it change our confidence? That level of hypothetical tuning allows us to then be accountable when that stock either returns or doesn't return as predicted. And that allows future hypotheticals to be far more informative and consent-based than allowed in simple binary predictors. I could say more about that, but I'll wait for you.
We're going to in a minute. But I want to just underline this. So I think it's easy to gloss over if you're a normal person, just go, okay. But imagine that you're a trader moving a lot of money, or that you're someone in a high-risk situation, and you actually, until now, kind of by the seat of your pants. Maybe it took 10 years on Wall Street before you really got it figured out, and then you have some sense of risk, but times change and you lose that sense, and you get wiped out. And so what Quinn has done on his own, I must say, with no guidance from, I don't think, anybody, except some Wall Street people.
A lot of good textbooks.
Yeah, and some Wall Street people.
Yes.
Is to not only accept that it's important to do this, but to take it down to a level that I don't think has ever been done before. Could you take us down to that level for a minute?
Okay, just use an example. I'm going to use a sciencey word, like post hoc. Most of these analyses are done post hoc. You do a bunch of predictions on some held out data set, and you form an empirical analysis of what the risk might be. The actual training on the engine itself, the one that's online with Pattern DE, takes the risk into account at each iteration of the model's development. So the models actually evolve to expose their risk surface. And because they are equations, the fact that they've evolved to expose their risk surface means that when you adjust those factors that it gives, like say 5 factors influence whether or not you should buy, you can do a hypothetical like, if this company had made $500,000 more return last year in its 12th, and then it passes the purchase line, and no other company has ever not shown a return that passed that line, now you have an equation that actually transparently tells you what its risk is. Now if SEC comes to you and say, why did you make that decision, it's a lot more defensible. And same with the EU, because they don't mind the fact that predictions can be wrong, but they want to know what you're basing your risk on.
So compliance
it's
issues.
built right into the mathematics.
Yeah. and taking it down to that granularity and that earlier step in the whole process, I think is unique. Is that true?
As far as I can tell, but Ben is the one that keeps up
Yeah,
on how
is it
unique
Ben? Is
things
that
are.
Quinn has done some amazing work at the interface of causal inference and conditional guarantees for finite samples for mathematicians and statisticians in the room.
See, they talk like this all day long, and I just listen. We really practice to avoid that kind of stuff. But anyway,
Well, I also want to give much credit to our two collaborative Wall Street.
not by name, but
Not by name.
type.
They've provided us with actual trading data sets they use in their day-to-day trading.
Right.
And that has made a huge difference because in order to be able to get these levels of confidence in the predictions that could be made and the profitability that could be turned, we've had to use real data, not just stuff off of Kaggle.
So here's our next announcement. Quinn's been working on this for a while with two partners we're not going to name. Both been in the business for decades. And Quinn, if I don't say this properly, correct it. But we are now at the point where we have high confidence that we could have helped them trade better using our new engine, RC engine. And we are excited about this, and they are excited about this.
Absolutely.
Okay.
Absolutely excited about this.
Thank you.
RCX AI is the future as far as I'm
Go
concerned.
RC. All right. Thank you, Quinn.
Thank you, Quinn.
Pretty cool. Angie. Angelica Walker.
Hello.
I think you're our second best dressed. Maybe your first best dressed. I can't tell. They're definitely like the dressing people and all of us others. How are you?
Good.
Great. What would you like to talk about today?
I would like to talk about some of our discoveries in the oncology space, specifically colorectal cancer. So we have been given access to one of the largest colorectal cancer data sets in the world, over 50,000 patients with hundreds of millions of single mutations in their genome from the Fred Hutch Cancer Research Center. And we applied our pattern discovery engine to find new discoveries within this genetic data set. So first and foremost, colorectal cancer rates are increasing rapidly for adults under the age of 50. Currently, the American Cancer Society recommends beginning colonoscopies at age 45, which means many young people are going to get cancer and have it progress pretty far before it's caught. So we, using our pattern discovery engine, have found 20 mutations that are all interacting together that we can screen to assign risk to individuals so that they can get their colonoscopy sooner and catch their cancer sooner, which is fantastic because this region that we discovered also contains a new drug target. For the longest time, biologists have considered microRNAs to be junk DNA, but we have recently learned that microRNAs are actually key to regulation of other genes. And we found a microRNA that is not expressed in healthy tissue and is only expressed in cancer and in fetal development. So we believe that this microRNA has something to do with the way that cells replicate. And this microRNA is perfect for targeting with a drug. And not only that, but this microRNA is expressed in other cancers other than colorectal cancer, including ovarian cancer, kidney cancer, lung cancer, breast cancer, pancreatic cancer, thyroid cancer, uterine cancer, glioblastoma, glioma, leukemia, melanoma. I could keep going. So
Wow. That's more than I thought.
And you know, when you see something like this, folks have worked in biomedical science. It is astounding. It's a once-in-a-career sort of thing to see a potential drug target that is not expressed in any healthy tissue. So you mess with it. You don't anticipate any toxicity because it's not doing anything in adult tissues. It's just expressed in cancer, and it's expressed in a bunch of cancers. The opportunity from Angie's discovery to have a targeted pan-cancer therapeutic with minimal or no side effects is tantalizing. So I'm incredibly excited about this. It's one of my favorite things that we've done. It's awesome.
Of course, there's always the problem of can you actually build it? Can you find a drug and then build it? That would probably not work, I would guess.
Okay. So we built it.
This is an announcement.
It arrived for testing at Lawrence Berkeley National Laboratory yesterday, and it is now in a freezer at -80, and will soon begin in vitro and in vivo mouse trials.
We just built a drug.
Yeah.
Pretty cool. Anything else?
Nope.
Well,
I hope it
so in
works.
summary, so this is a multi-year project. It's a huge beast of a data set. It's been really difficult to work with. We appreciate the Hutch help working with us on this. Angie's been running this for a while now, and to very quickly, I would say, from our experience, to go from 0 to 60, where here's the set. Okay, what is it? All the way through the process of identifying the patients, increasing the predictive value for the global question, which is what they wanted at the Hutch. We did that. She did that. And then going into all the steps you just described. And then you got like the under 42 years old, and we did that. And then it's like we 200% improvement in predicting for those people who are younger. We did that. When I say we, I mean you. And then recognizing the geography of all of this, and suddenly saying there's a part of a chromosome, and here it is, and then actually hold everything. It's part of microRNA. Here it is. It's part of the microRNA. It's not the whole thing. Here it is, and then that means we can build an antisense to that, and it's a drug, and the drug is in the fridge.
Drugs in the fridge.
Well done. Really cool. Really cool. So thank you, Angie. You are relieved of your duties. I guess.
I
don't
stay
know.
here.
No, you're staying, aren't you? You're
Yeah.
staying. I'm the last to figure these things. So what we'd like to do now, a couple of things. One is we would like to encourage you to participate with Pattern. You pick how. If you'd like to be a partner, Denise, as you can see here, Denise Hudson, send her a note or see her. She's at the table outside most of the day. And great. If you're interested in learning more about Pattern and just maybe investing, we are built on the interest of fire people. It's pretty interesting. About 87% of all the funding that has come to us over these 10 years is directly or indirectly because of fire. And in fact, we were born on this stage. So we actually have a picture of that, and it's going to be up here in a minute. Here's the invitation. So if you would like to join us this afternoon from 4 till 6 back at the Hyatt, you need to tell Denise or Laura, and they'll be in the hall. And there's a seating capacity, basically. It's a suite. So they'll tell you what suite it is, and they'll tell you how to get there and what time, which will be on the 3:45 bus, and we'll see you there, as long as we have room. So let them know if you'd like to go to that. We have an ongoing list, so maybe you're already on the list, but make sure you are. And then we'll see you. This is going to be fun. So informal, not a program. But what we will do is we'll have the prospectral device there, and we will have you there doing Pattern DE to show you what that looks like in real time. So, or Quinn, somebody will do that. And we'll have drinks and things to eat and so forth. And we'll go straight from there back to Scripps, where we'll watch the sun go down. It won't be raining, and then we'll see VR things about coral out in the wild somewhere, and it'll be totally interesting and beautiful. And the sun will go down. So and then we'll bring you back. So anyhow, we're kind of at that point. We would love to have your help in whatever way you'd like to help, and your participation. And what we want to do is, do we have that photograph again? Well, we were born here, and when we were born here, it was 2015. And our foundational story is that, in fact, this was a CTO challenge back in that year, and there were about 10 people who were CTOs, and they stood on this stage, and that became Pattern. And but by the time they walked back to the coffee room, we had been funded and staffed, at least the first staff. So there we are, 2015. Now it's 10 years later, basically. And I'd like to ask our team to come up. And if we have a photographer here, right there, come on up, guys. We're gonna do a redo of that picture. Stand up. Are we good?
Everybody ready? Okay,
Yeah.
big smiles right here, everybody.
Cheese.
Beautiful, beautiful.